Everybody, welcome back for the semester. So thanks for joining us for the first seminar of the semester. Today we have Peter Lynn from Otherlab in San Francisco giving this talk. Introduce Pete here. So Peter Lynn is a mechanical engineer working for Otherlab in San Francisco on early stage research and development, mostly in the energy and robotics realms. He's originally from New Zealand and was once a kiteboarding pioneer and kite designer, through which he developed an affinity for the ocean. He has delved into wind energy, solar energy, thermodynamic systems, inflatable robotics, and drones. Peter has a broad exploratory theoretical background with a strong practical bias towards prototyping and testing. So, take it away, please.
Thank you, Zach. Yeah, I suppose I should give just elaborate on all that a little bit. I grew up in New Zealand. I suppose I was water skiing behind kites 35 years ago. But about 25 years ago, I think I did my first bit of upwind on a kiteboard. And that was kind of the first time we'd sort of done that and sort of figured it might happen. Admittedly, that particular run was on a mountain lake with strong turbulent winds, and ended in a gust which sort of took me up into the air about 10 feet or so. I was kind of a little bit scared and I didn't land it. I landed on my belly and then sort of body dragged back to shore. So I was a little bit weird about it. But, you know, 10 years later, we're sort of happily jumping 30 feet in the air and not really thinking much about it. Anyway, from there, I sort of transitioned to, I joined a airborne wind energy company in San Francisco called Makani Power that was working on trying to generate electricity from using basically very large kites as wind turbines. And then from there, I went on to a company called Otherlab in San Francisco. And Otherlab is kind of a small company that does early stage research and development. Sort of model, we're sort of a little bit of an incubator, but not really, because it's sort of all self-driven. So our basic business model is that we usually get government funding to start some new weird project and then sort of eventually spin that out into some company. And here's just some of the things I've sort of worked on over the years. Yeah, inflatable robotics. I didn't have so much to do with the CNC stuff, but we also did, there was a small CNC milling machine, some laser cutting. One of those projects is a gas tank for hydrogen, conformal gas tank. Then there was sort of a whole lot of inflatable actuators that turned into a solar company for doing single axis tracking, various drone stuff. One of the main focuses of Otherlab is energy. We've been funded by ARPA-E multiple times for many different projects. And the founder of the company, Saul Griffith, wrote a book called Electrify about sort of how to electrify all our energy use. And that sort of helped inform a lot of the Inflation Reduction Act. Anyway, there's a very, very strong energy theme behind a lot of the stuff. So under the ARPA-E program, which is a part of DOE, there was a Mariner program. And this is what got us involved with UNH and another company called Umaro Foods. Well, they used to be called Profit, with Beth Isotta, who is doing seaweed-based bacon, sort of plant-based protein. So the Mariner program was set up to try and create large-scale microalgae farming or seaweed farming and using that for biofuel production. And there are a couple of sort of effective requirements of that you had to get the cost down, dry time that is, and that had to somehow sort of create a revolution in aquacultural seaweed farming akin to what we see in terrestrial farming. At the moment, seaweed farming in the US is people hanging out sort of one line at a time and harvesting it by hand with a knife. It's pretty much at the single furrow plow level being pulled behind an oxen. It's sort of at that kind of level. And for all this to get interesting, somehow we need to be able to do that at sort of many thousand acre farm scales with large machinery that is like 60 feet wide to compare with, say, a combine harvester, and basically all of that type of equipment where one person can farm a large area. And as soon as you want to get to that scale, you have to go offshore because you run out of protected waters. And that means you have to deal with large waves, 50 foot or so, which makes life a lot more challenging. So some of the benefits of seaweed farming, in lab environments, multiple species have achieved up to 100 dry time per hectare yields per year, which exceeds pretty much every terrestrial plant, with the possible exception of sugar cane, which is a C4 plant, but that only works sort of in warm environments. The other sort of weird benefit of that is that when you sort of grow seaweed in the open ocean, it can actually have a beneficial effect on the ocean. If you're farming on land, you're effectively displacing natural habitat. In the ocean, you're kind of creating a nursery and actually helping fish production in many cases. The other interesting thing about the ocean is that below about 50 to 100 meters, you effectively have an unlimited source of nitrates. So you do not need to pay for fertilizer if you can access that. And if we could displace or substitute around 20% of all of our land-based agriculture with seaweed, for example, most animals are happier with up to about 20% seaweed in their diet. That's somewhat limited by the effective salt content. To go above that, you really want to start removing salt from the seaweed. And there are some processes for doing that, but it's a little bit more involved. There are actually a lot of species have actually at different times lived off 100% seaweed diets. Cows, I think chickens, pigs, sheep, goats, and various weird places around the world. Anyway, if we could substitute about 20% seaweed, then we could effectively negate the need for adding inorganic fertilizers onto land, because the effluent produced by those animals can basically bring all those nutrients back up to that level. And at the moment, we have a weird thing that we take all these nutrients off the land by effectively producing food that we then eat, and then through our wastewater, that all gets flushed out to sea. And there's a process there that we're continually depleting nutrients from the land. Ideally, we want to be able to close that loop and bring all those nutrients back from the ocean onto the land. And seaweed farming is a way to do that. So there are two sort of primary innovations that we've been working on at the Otherlab end. At the UNH end, sort of the two innovations that have informed this project have been the composite lines instead of traditional sort of polymer-based lines. The advantage of the composite lines being that they have sort of a minimum bending radius, so for whale entanglement and other things, they'll actually break. So it's sort of driven by that largely. But there are a few other benefits. And the other one is sort of the structure of the farm that gets loads to the seafloor as quickly as possible to minimize the required structure so that it can survive in larger waves. Anyway, the two innovations from the Otherlab end are sort of this anchoring robot, which is really just, I suppose, one way to think of it is it's just a very large electric screwdriver for underwater. And this enables us to screw in helical anchors. And maybe there are other applications. But I'll go into that in more detail shortly. And the other device is an upwelling system. Traditional upwelling systems have consisted of a pipe and a pump, often wave power. But this is a way of doing it where we have a very large rotor, which is suspended beneath a wave float. And as that moves up and down, the blades flap around, sort of like a wave glider, and create a large plume of water that heads towards the surface. But these rotors can be very large diameters, so the one we've tested so far is about 100x the flow rate of what a traditional upwelling device might be. and yes, it can create sort of a jet of water that then pushes towards the surface, and you can get up to about 10 diameters in terms of that projection. So a 10-meter diameter rotor might be able to send a jet of water 100 meters up, so it might be able to operate from 100-meter depths. Yeah, that's probably enough about that. Okay, so the interesting thing about the ROV is, well, the interesting way of doing it is that traditionally helical anchors, when they are installed underwater, they're done with sort of a hydraulic rig. Sometimes on the end of an excavator, if the water is very shallow, or if it's a bit deeper, they'll actually lower the hydraulic rig to the seabed. That's sort of a big, it's a bit of a pain of a process, but it works somewhat well, and it's done extensively in New Zealand and other countries, but not actually in the US at the moment. And they're installing 25-ton pull-out strength anchors to about 100-meter depths, and they cost about $2,000 an anchor in that range. So our particular insight was that drones, if you just turn the rotors around, you can get all of your navigation position control, and also you can extract very high torque from them. So we just orient the thrusters so that the ROV spins, and then it can drive large anchors into the seabed. And typically, well, at larger scales, the ROV actually ends up weighing less than the anchor. But the nice thing about electric drive systems now is that they're incredibly powerful, and you can avoid all the hydraulics and everything else, and you can get a very high degree of controllability at very low cost. So nominally this has a tether and is powered that way, although you can actually operate it untethered in some cases. So helical anchors are kind of interesting. There are a couple of anchors that can achieve the very high pull-out strength to weight ratios, but the other types are sort of related to the drag and bendment, but they actually turn into sort of have a wire rope and a plate that effectively locks in position. But traditional drag and bendment anchors are sort of highly problematic for high loads because you have to have very large vessels to proof load them and install them. But the helical anchors do not. So they're capable of very low costs, very high pull-out strength ratios. They're also capable of vertical loads. So a traditional drag and bendment anchor is not so good at vertical loads. And a lot of applications, at the moment, a standard traditional anchoring approach is to have some kind of drag and bendment anchor, and then a long length of chain, and then a long scope angle, and then whatever it is that you're mooring. If you can have a vertical pull-out, an anchor that can take vertical loads, then you can change that and use a submersed buoy, sort of aligned to a submersed buoy, and then to your system. And that ends up being much, much lighter, and it has much, much less impact on the seabed. You do not need to use chain because you can use a buoy to do the tensioning. It's sort of an inverted catenary, if you want to think about it that way. And a steel ball or a steel submersed buoy is like 1/10 the weight of steel chain for a given force, buoyancy force that it exerts. And it's just sort of a lot cleaner all around, and you can have much, much lower effective scope angles. So your total mooring footprint is much, much less. Standard anchors are typically good for 20 years. And another nice thing is there is a torque to installation strength, to pull-out strength relationship. So you basically embed these anchors until you reach a given torque, and that gives you high confidence of what the pull-out strength is. That is very nice because you have much lower risk of pulling an anchor out. And there's another possible trick we can do with the ROV is that we can probably put a rock auger on it and actually pre-drill holes in rocky soils and perhaps even bedrock eventually, which would allow us to be somewhat agnostic about the seabed. And that is something that we'll be testing soon. We've also experimented a little bit with split shaft anchors. This enables us to do multi-line anchoring. One of the anchors that we installed off main had 4 shafts coming off it so that it could take loads in 4 different directions. That's just sort of a weight saving system. cost saving. And there are also helical piles. We have not really got into this yet, but if you have a large diameter shaft up top, it greatly adds to the weight of the anchor and cost, but enables you to take lateral loads directly without bending. With a standard helical anchor, you actually just load it up and the shaft just bends to its given position laterally. You put it in vertically and just bend it over. That works well when your loads are in a single direction all the time, which is typical of sort of an aquaculture farm or various other applications, but it doesn't work for swing moorings. So, but in this case, you can use a helical pile, which can take those high lateral loads, and you can create swing moorings that way. It does add to the substantially increase the mass of the anchor and cost, but it is convenient. And there's a type of anchor here that we wish to experiment with, but we haven't done so yet. The one in the picture that sort of looks more like a wood screw, where it has a small thread, and many of them, and it comes to a tapered point. In terrestrial applications, that style of anchor tends to be much more forgiving of rocky soils and much easier to get started and use. But at this point in time, I do not know how well characterized they are in terms of pull-out strength. So that is something that we'll investigate. It could well be that that's the type of anchor you would want to use in Alaska, for instance. There's also a lot of interest in composite shaft anchors. If we can go down that road, we basically get the weight down by like 3x or so. The cost probably stays about the same, but the longevity probably increases to maybe 50 years. And that would also just be a lot more convenient from a ship handling and installation perspective. Okay, here is a video of the first ROV we did. Actually, John Pomper built this one. He's currently at ReefGen trying to make robots to plant eelgrass and coral. But this was one that he developed. So we have this is obviously the first proof of concept prototype, but in principle, you can move the anchor to wherever you want. You can angle it if you want, and then you can just spin the ROV around to put the helical anchor in. Sorry if that's slowing down a bit. Oh, sorry, it's buffering. And then once the anchor is in place, you can, here it's actually doing a, just pulsing to get a bit more torque out of it because it doesn't have a huge amount of torque. But that's kind of the limit of its torque. But then when you're done, you can just sort of detach the ROV. Sorry, it's buffering again. And we can have the anchor line sort of pre-attached to the ROV, so we can remove it with the anchor line already on. Sorry, it's a little bit jammed. Maybe, yep, there we go. Right, sorry, sort of skipped that bit a bit. But anyway, so we can put in an anchor with a line already attached. Okay, so that was the first prototype. This was the second one. This was scaled up to, this one used electric outboard motors that were sort of modified to use underwater. And this one installed these larger anchors, and we pulled out some of these at about 1.2 ton, just off the dock. So fortunately, our house has a dock, and during the pandemic, we were able to do our testing just off the back. Very convenient. This was a bigger ROV that we developed. This was very much a rush job, so it didn't have everything sort of dialed in. Again, we used the electric outboards and this motors adapted, and unfortunately that was sort of a major failure point. So this one installed 3 anchors off main. One of them was a split shaft anchor. Actually, that one shown on the right is a 4-way split shaft anchor, weighed about 200 kilograms, I think. The ROV itself weighed maybe 60 or 70 kilograms. 2 people could lift it. The arms will fold up and you can sort of carry it. So one of those anchors, I think we installed one to a depth of about 17 feet. This one we embedded to a depth of about 11 feet, and I think it got pulled out at about 11 ton of load with lift bags. So we sort of were torque limited. We ended up only getting about half the thrust out of the thrusters that we needed to do full installation, and water started getting in and we ran into issues. Anyway, we're now building a next iteration ROV. This is back at smaller scale. This can only do about 5 ton pull-out strength anchors, but it's much more refined. Well, the intent is to have it much more refined from an operations standpoint. Uses carbon fiber struts or arms for the thrusters, and these are actually profiled and they're oriented at a pitch angle so that when the ROV rotates, it generates substantial downforce. Long term, ideally, they want to have independent pitch control so that we can set the downforce independent of the rotation speed somewhat. So this one, hopefully, we'll be able to carry it on an airplane as checked-in baggage, and it'll just we're going to spend a whole lot more time integrating like acoustic GPS so that we can do accurate positioning and working on the stability, so it's sort of a lot more autonomous. One of the nice things about these particular approaches is that long term, there is a direct path to autonomous operation. So applications for this technology, seaweed farming, obviously, which is a greater than 10 billion industry globally, although in the US it is still very much at the boutique farming scale. Interestingly, China and Korea pretty much use all of their protected water areas for seaweed farming. They now have to go offshore if they want to expand. Mussel farming in New Zealand, they're installing over 1,000 anchors a year, but that's with the hydraulic systems. So obviously there's all those areas, all those aquaculture applications. Mooring for buoys and boats, a lot of instrumentation, navigation buoys, that's probably $1 billion market with all the boat stuff as well. You're probably looking at more helical piles there if you're doing swing moorings. Floating solar is getting big in Asia and Europe. I think it's already in excess of $1 billion a year market. It is not so big in the US because there's a lot more land available. But if Europe wants to go self-sufficient in energy, which it needs to at the moment, then it's going to have to start doing a lot of floating solar because they have little other area to use. Indeed, they're even looking at offshore floating solar in the North Sea, which I think is very interesting, challenging. And one of the biggest markets is fixed and floating offshore wind power. Floating offshore wind, there aren't many floating wind turbines installed yet. There's only a few. Otherlab actually has another spin out in that space that is developing a floating offshore wind system. But there's a huge market for the fixed offshore wind. And there you may well be using helical piles. One of the nice things about the helical piles is that they make much less noise when you put them in. And noise is a huge issue at the moment. There is effectively a kill radius for fish around the pile driving at the moment. And there's one interesting application long term is we can probably do dynamic anchoring. At a certain level, you might just have multiple ROVs with integrated anchors on them. And if you have a ship or construction boat or whatever, you'll be able to just send these off and they'll automatically anchor themselves and retract themselves. And that would greatly speed up a lot of construction processes. And also because you get to do verification of your load capacity via the installation torque, you can have high confidence in your anchor strength and you can do it in a much less environmentally damaging way. So next steps, we have to complete this existing ROV that we're working on that will hopefully be in the water over the next few months. Contract sort of winds up end of June. And we'll hopefully get into installing a few anchors in a few different places around the country. After that, we hope to scale up to a 25-ton scale, but that will require next round of funding. At the moment, it's costing a few $100,000 and 3 to 6 months to sort of build an ROV. So that's kind of our time scale. And then after that, obviously, getting up to the wind turbine scales, which is a many billion-dollar market. Okay, the other innovation is the upwelling device. When you look at the global oceans, they're basically mostly deserts, and that's because of the lack of nutrients in the surface water. If you look at the scale down the bottom there, that is logarithmic. So really most of the productivity happens in the few natural upwelling areas and in sort of coastal areas. The basic reason for that is that phytoplankton at the surface absorbs all the nutrients, then dies and sinks. And there's no easy way for those nutrients to get back up. So that effectively just kills everything off. These are just some rough profiles I did for different places. So Alaska Inside Passage, you can see here by this plot that as soon as you go down to like 50 meters, the nitrates just go way up. At about 2 micromole per liter, that's sort of about the point where seaweed stops growing. Phytoplankton can go a little bit lower, but your sort of nutrient, you really want to be up around 10 to 20 if you want to not be nutrient limited. Now, along with that, you get the sinocline, which creates a density gradient, which is a density gradient. That creates sort of a gravitational potential energy that you have to pump against. So for upwelling, you basically have to overcome that gravitational potential energy, and that sort of sets the power and size of your system, and the kinetic energy you have to put into that flow. Here's similar plot for California, different places, which is sort of a natural upwelling site. So the nitrates are a little bit higher, but again, by 50 meters, you're getting pretty high nutrient levels. And Gulf of Maine. And in the winter, this is obviously very seasonal. In the winter, there's almost no density gradient. So upwelling, it's very easy to pump a lot of water. And interestingly, during the winter, you can actually pump more nitrates than during the summer. Even though the nitrate gradient is much lower, your flow rates can be 10x higher because that density gradient is just so much lower. And also your available wave energy is higher. So this is just a representation of the device. Here, we're sort of putting solar on the platform as well, because again, it's almost sort of doubles your upwelling power during the summer, and during the summer is when you really need it. In New England, especially, the wind and wave climate during the summer is much lower, and the need for upwelling is much higher. Seaweed grows during the winter, it doesn't grow through the summer. If you can just grow year round, you're just dramatically increasing yield. And we also put tip thrusters on the blade tips. That enables us to convert that solar power directly into rotation. And that also gives you the ability to do cyclic control, which gets very interesting because it means that you can tilt or pivot the thrust vector from that rotor. That enables you to do active station keeping. It also enables you to convert ocean currents into upwelling. It took us a long time to sort of converge on the 3-bladed configuration, which is more characteristic of sort of a wind turbine. Initially, I was looking a lot at single-bladed systems, which were basically similar to underwater kites, or sort of related to the McCartney system of airborne wind energy. The advantage of the single blade is that it's obviously a lot smaller, it's a lot easier to pack and move around the place, but it's just the dynamic instability is less forgiving. You have to sort of actively control it. The 3-bladed system is just very robust from a stability perspective. And I sort of had a test rig that I developed for operating off the dock that would just move up and down with a big sort of lead screw and servo system. Well, it was a brushless motor. And yeah, I sort of had that somewhat instrumented so we could measure the motion and the loads and sort of characterize these systems. It was effectively mimicking what a wave would do. Here is, this is actually in the wave tank at UNH. And as you can see how the blades flap up and down with the pulse. This pulls a lot. You can basically, this is a 1.5 meter diameter prototype, and you can put as much force into that as you can. Yeah, it pulls a lot, and you can see the upwelling plume that it produces. So from there, I was trying to do, first tried to build a 15-meter diameter rotor. It ended up being very inconvenient, especially as I built it during the pandemic, and I was trying to do everything by myself. Sort of one blade or arm was about at the one-person lift level, and it just became a nightmare. I actually tried to test it off the dock at one point, and then the tide changed, and I got it caught under the dock in about a 1 meter a second of current, which was quite interesting for a couple of hours trying to get that out. So with that in mind, I then built a smaller 7.5 meter diameter rotor, which was much more manageable. This rotor folds up and winches up in between the hulls of a catamaran that we sort of made. This catamaran is foam-filled aluminum skin. It is, in principle, the crush depth of the foam is, I think, 20 meters or so, but we've never really submersed it. And yeah, that was. But the other thing about that catamaran shape is that it was flat bottom, so it had about 7 square meters of direct area, because we're actually trying to maximize the loads from waves, or the motion from waves. So it's a very different design to what a normal boat would be. But one of the side benefits is that it actually planes, so we could pull it at speed out for testing, which is kind of fun. Here, just a couple of quick videos. The testing of this rotor. This was just pulling it up and down by hand, so sort of almost a rolling type position. We could get it rotating around, and that was sort of how I was checking angles of attack and other things, that it wasn't stalling. This here is when we put tip rotors on it. It's just spinning around, and we were just, again, one of the nice things about this setup is there's a load cell, so I could actually back up this. And there's an IMU on the rotor, so we get speed, rotation. You can sort of see it a little bit. That's just off the end of the dock. Okay, so we then tested it at Moss Landing. So you can just see the rotor in this image, in this video. It's at about 4 meter depth. And then as we back out, you can see that it is generating an upwelling. This was in flat water. It was pulling about 140 kilograms or so. And as we back out, you can just see the upwelling that it's producing on the order of like 25 meters down. We were still able to see this surface plume when it was down at 8 meters, but about 12 meters was getting a little bit hard to see. We just didn't quite have enough time. On another day of testing, we were out in about 1 meter waves, and we had peak loads getting up to about 500 kilograms or so. It was actually starting to submerge the end of the float of the catamaran. It was nominally designed, the rotor was designed to have higher load carrying capacity than the displacement of the wave buoy of the catamaran. So in the worst case condition, it would submerge the entire float and mitigate the loads that way. Because if you have a storm where you have 5 meter waves, the scaling is sort of a square relationship, and it's just, yeah, you're going to destroy everything if you don't submerge. Okay, so the flow rate from that particular system, you can back it out directly from the thrust on the rotor via sort of actuator disk theory. So we were getting about 5 cubic meters a second of flow rate, just under that thruster power. So each of the tip thrusters was about 1 kilowatt, so we had about 3 kilowatt total, but really only a couple hundred watts of that was effectively being delivered because of the propulsive mismatch. The blades just weren't going that fast. If we do drag reduction, a few other things, they'll line up a lot better. So that upwelling that we showed, that was really only with about 200 or 300 watts of input energy. So we talked about most of that stuff. The upweller, the rotor itself, nominally scales to wind turbine sizes. Because it is bridled, you get about a 10x saving in structure by doing that. The traditional problem with underwater turbines versus wind turbines is that the fluid medium is 800 times more dense, but the effective speeds of those flows are also about a tenth. So if you take a wind turbine and put it underwater, instead you sort of transition from a 10 meter a second wind to a 1 meter a second current for about the same energy, but the loads on that underwater turbine are 10 times higher, and the rotational speed is 10 times slower, and the gearing you need on that is also 10 times higher, which basically means that your gearbox costs 10 times as much as well. And that's sort of that fundamental difference. As the sort of saying goes, there's more energy in the wind flowing under the Golden Gate Bridge than there is in the current flowing through the Golden Gate Bridge in San Francisco. So because of that, the bridling basically enables you to get back to that same scaling relationship as wind turbines. So we could potentially make these underwater upwellers at 200 meter diameters, bridled, and at that you get flow rates which are in the 10,000 range, 10,000 cubic meters a second range. And your costs will roughly scale similarly to wind turbines. So that is achievable. So the applications for the upwelling device. Well, the immediate ones are obviously you can grow seaweed year round and greatly increase you're basically fertilizing the seaweed, so your yields just go up dramatically. You can probably do 3 to 4x increase in yield. This is also probably helpful for a lot of mollusks like mussels and oysters, because often the stuff that they eat is at greater depth. It just sort of depends. And with finfish, you can bring cool, nutrient-rich water up, so that cool water helps a lot with disease and all sorts of other things. One of the big applications is probably ecosystem restoration, because we can effectively create bring a natural upwelling, well, it's an artificial upwelling to areas. We can greatly increase biological productivity, but we can also bring all that clean, deep water into the surface and flush out sort of pollution and other things. We can probably protect against warming events, so we can stop coral bleaching if you site this near coral reefs. Probably you have to site them up current in a place which is a bit deeper, and you can actually use the geography to effectively upwell shallower areas which would not normally have all those nutrients. For example, if you take a bay where water is flowing in and out with the tide, if you upwell on the incoming tide, you can effectively turn the entire bay into a one-way positive displacement pump and just continually upwell it. It's come to light that we can probably do carbon removal for about $10 a ton of CO2 using direct upwelling. And that's just through the increased biological productivity, the phytoplankton increasing and eventually getting synced in deep waters further away. Some proportion of that phytoplankton bloom ends up in the deep ocean. But that is something that we need to explore, and we really need to do field testing. This is something that needs a lot more research. Another interesting aspect of the upweller is that there's an effective multiplier between the power in to the cooling effect of the water it brings to the surface, and that's on the order of 100,000, which is a huge lever. So a 10 megawatt upweller can normally produce around a terawatt of surface cooling. That starts to get significant globally. Global incident solar radiation on the Earth is about 80,000 terawatts. On that was 88,000 on that order. So you can imagine a farm, a 1 gigawatt farm of upwellers that's starting to get to a level where you could influence or control things like the Gulf Stream. You could have an effect on global currents and make sure that they didn't do bad things. Obviously, if you do a lot more upwelling, we can greatly increase the biological carrying capacity of the oceans. And that means we could bring back whales and other things. I mean, each upweller has sort of a little bit of a marine animal entanglement risk, but the benefit from increased food production from it probably more than outweighs that risk. And that's something I need to figure out how to quantify. You can probably do direct hurricane mitigation just by cooling the surface waters. So insurance industry might be interested. So yeah, with cyclic control, you can generate a huge amount of thrust at low speed because it can convert that wave energy into through that. It's basically a very, very, very big propeller. So that brings in possibilities of just station keeping offshore. You can basically create virtual anchors. You can pull big seaweed farms around, whatever. I should just probably wrap this up. So there are some weird geoengineering benefits that this may have. It's possible that a couple of $1 billion installed basically between Greenland and Iceland could slow currents or block currents moving in and out of the Arctic. If you did that, the Arctic would basically freeze over. The albedo increase would reflect a whole lot more sunlight back into space, and you would stop global warming. So for as little as a few $1 billion, you can probably stop global warming. But that is sort of geoengineering, and it's not what I would advocate. But it is an option if we run out of options. And the nice thing about that is that if you are going to do geoengineering, you really need to do it in a way that is highly controllable and highly reversible. And if doing it this way, you can play it by ear, so to speak. You know, you can put in an upwelling unit, see what the effect is. If you don't like it, you can take them out in a couple of days. Many of the carbon removal systems are working on 100-year lifetimes or more, and there's really just no way, there's no undo button. So if you are going to do geoengineering, make sure there is an undo button. It's just one thing I would say. But the more benign approaches are, you know, what we really want to be doing with the upwelling is doing it via increasing the ocean productivity. And that can absorb a lot more carbon. And if you're going to remove carbon, by far the best place to put it is in living organisms, because that increases the natural habitat and increases biodiversity. Indeed, if we just restore global habitat, then that largely actually fixes climate change as a byproduct. To go into that a little bit more detail, 10,000 years, we currently farm half the world's productive land. That transition to agriculture probably released carbon on the order of all fossil fuel releases to date. So that's probably a large part of their problem. If we can just reduce our terrestrial farming footprint by about 20%, that probably keeps us under 1.5C. And if we do that, there are about 10 different ways of doing that I can think of. And one of them is if we can just transition most of our animal feed or 20% of our food for people and animals to seaweed, then that probably can keep us under 1.5C. And of course, greatly boost biodiversity and natural habitat, bring back the whales. There are just a whole lot of benefits from doing that. And that's kind of the preferred way, I think, of solving this problem. So next steps, we basically have to figure out how to validate the upwelling closed loop on the biological effect and determine if there are any weird impacts, unknowns that we need to avoid, or whether they can be mitigated, figure out what the effects of geography are, because different places will work better than others. One of the things that when you upwell is you also bring carbon dioxide to the surface along with nutrients. So that ratio of nutrients to carbon dioxide has to be positive for there to be a net carbon removal benefit, because you have to create phytoplankton that then take that carbon dioxide back down again. And yeah, we really just need to do a lot more research on quantifying what those impacts are. But the upwelling device, it is a huge lever in terms of a very small amount of energy input has a very large effect on global climate change. So if you want to find a very small lever for shifting the world, dealing with ocean currents is one of them, or with nutrients and thermal gradients in the ocean. That can have by far the greatest effect for the minimum input. And at that, I'll probably move on to questions.
Questions?
Hi, Pete. I don't know if you can see us, but that was a really interesting talk. I am interested in the underwater, the ROV that drills into the ground. What kind of tether management system do you have on that so that it doesn't just coil your tether while it's underwater, or do you have to spin in the opposite direction on your way up?
Yes, that is quite, yeah, it is a little bit of a challenge. So at the moment, how we've done it to date is we really just tie the mooring line onto the top of the ROV and put a little buoy on it, and then we're actually just taping it. And then when the ROV releases, it sort of breaks that tape, and the mooring line just drifts and floats to the surface. On this version we're doing now, we're going to have the previous version, we had a rotary electrical connector on the ROV and also a tether swivel. This next version is going to have that on the surface, and we're going to actually spin the whole tether drum. So doing that, we can actually just sort of strap the mooring line to that and rotate everything at once and clear it out. We also have the capacity, because the ROV comes with its own IMU, it's all sort of hobby stuff. It's very easy to add a high degree of sensing and control. We can basically bring it back to the surface by maintaining its orientation. So if we're doing multi-lines, like 4 anchor lines, we can stop them from twisting up. There are some tricks there. But yeah, it is being able to install anchors and their anchor lines without divers is one of the primary benefits of the system, and potentially to do that to 1,000 meters if you want. This particular ROV we're building now is nominally rated to 200 meters or so.
Excellent, thank you.
Pete, how about the bottom morphology? How much down thrust do you need for a harder bottom, and does that impact the angle of your thrusters and the blades, or the thrusters that the ROV can push down?
Yeah, so downforce, yeah. Yes, it's a big function of the type of anchor. So you can actually make anchors which don't need a lot of downforce. The traditional helical anchors, they tend to work better if you have a higher downforce because it disrupts the soil less. But there's sort of a price to pay for that. But we, like this particular ROV here, which is about 3 meter diameter, it will nominally be able to apply about 500 kilograms of downforce when it's spinning at full speed. And yeah, that's enough to get through most things. But that sort of screw type helical pile, if I can show that, this one here, that one you can probably get away with much lower downforce, hardly any. And it will be able to go through hard surfaces and rocky surfaces. But then, of course, we get into the rock auger side of things. And yeah, we should have enough downforce to be able to operate a rock auger. And that enables us to pilot holes that we can then feed an anchor into. And because we have the precise positioning, we can drill a hole and then put an anchor into it, which is otherwise not something that's easy to do.
Thanks, yeah.
I'm curious about the economics of this. Obviously, it takes someone who's willing to invest in it and sees seaweed farming as a viable activity. In the places where seaweed farming is more prominent than the US, who's investing in it? Is it private individuals? Is it government as part of national policy? Is it private industries like insurance companies that are trying to diversify? What are the economics behind it?
So the economics behind seaweed farming, sort of high level, the people feed market is like $10,000 a ton, dry ton. The animal feed and fertilizer market is about $500 a dry ton. And then for biofuels, we'd have to get down to about $100 a dry ton. Each time you go down, you sort of increase the market size by about 10x. So the fertilizer and animal feed market is like 10 times bigger than the people market. Most of the seaweed grown in the world is for the people food market, and that's really just private farmers. They've been doing it for hundreds of years in some cases. Then you get the big industrials, multinational organizations, companies that are doing industrial chemicals. Then there's a lot of seaweed farming in like Indonesia and Philippines for those markets, and that's for producing like carrageenan, agar, and I think a few other industrial chemicals. And that's also done at large scale. But again, the farms tend to be locally owned and operated, but yeah, they produce for some of the big companies.
Thank you.
In the US at the moment, it's all just small private farms. One of the things that we need to do in the next few years is we need to get someone to put in 20 million or so to build the first terrestrial farm, scaled seaweed farm, that we can start testing out all the scaled up equipment we need to farm seaweed at scale. So we need to be developing the equivalents of combine harvesters and tractors and drilling systems that work, or seeding systems that work at these much larger scales. Probably we need to find some multinational like to make that punt, because if we can do that 10-20 years from now, that's basically an industry that could be 10 or 20% the size of the agriculture industry in the US. So yeah, we need someone to do that, but probably happen.
Great question.
One last one. So about the Upweller, you mentioned that it was designed to be submerged in larger storms. Did you mean that in the presence of larger waves, it'll be pulled underwater by the propeller, or it can be like someone would go out before a large storm and allow it to be submerged completely?
Yeah, so the submergence of the Upweller and big waves. Yeah, it's you sort of have two choices. You can either do pitch control or governing of the rotor blade so that the float can ride up and over big waves, or you just submerge the whole buoy. And that's actually by far the easiest and most effective load limiting system you can do. So you just, as soon as the waves get above about 2 meters, it will start submerging the float. Because that rotor can pull many ton very easily. It's a very large propeller. So it just directly and passively submerges the buoy, and you don't have to do anything. Admittedly, the current float, the swivel on it and instrumentation system is not designed for submergence, but the hull and everything structurally is. Although it's probably all unstable, but yeah, I need to do something about that. But yes, in big waves, it will just passively submerge. The loads that the rotor generates are a function of how fast the wave moves up and down, and as soon as it goes up, it's sort of a least a square relationship. Yeah, it will just start submerging.
Does that introduce any amount of snap into the tether, or like what connects the rotors to the float?
Not really, because the rotor is passively weighted. It has to have ballast added to it so that it can go down faster than any wave goes down. I mean, the blade's feather, so it basically dives down. But it needs to, you have to add ballast so that happens. But the tether should always be under tension. So yes, it's going to cycle a lot, but it will always be under tension. And there's a bit of the load doesn't go up that dramatically because the blades are also picking up speed. There is an inertia to them. They don't start generating full lift until they're at high speed. And that's also going on.
Interesting. Thank you.
All right, any last questions before we wrap up? Okay, well, thanks, Pete.
Thank you.